Thermodynamics. Now, thermodynamics, it is really I think, in my opinion, it's a very nice topic. Obviously, a bunch of definitions you have to memorize. The Born Harbor cycle probably isn't the nicest one, but then the rest of it, entropy change, Gibbs free energy change, all of that, it's really memorizing the equations, units, and being able to rearrange them quite well. And yeah, it's just a lot of learning stuff. So thermodynamics definition of enthalpy change of formation. This is just a review. Enthalpy change one model compounds form from its elements in standard states under standard conditions. Enthalpy change one model compounds form from its elements standard states under standard conditions. Bond dissociation enthalpy change when all the bonds are the same type in one mole of gaseous molecules are broken. Enthalpy change when all the bonds of the same type in one mole of gaseous molecules are broken. Enthalpy change of solution. Enthalpy change one mole of solute is dissolved in enough solvent so that no further enthalpy change occurs on further dilution. Enthalpy change of atomization of element. Enthalpy change one mole of gaseous atoms formed from an element in its standard state. Enthalpy change of atomization of compound. Enthalpy change one mole of compound in its standard state is converted to gaseous atoms. First electron affinity. Enthalpy change one mole of gaseous 1 minus ions formed from one mole of gaseous atoms. Second electron affinity. Enthalpy change one mole of gaseous 2 plus 2 minus ions is formed from one mole of gaseous 1 minus ions. Enthalpy change of hydration. Enthalpy change one mole of aqueous ions is formed from one mole of gaseous ions. Lattice enthalpy formation. Enthalpy change one mole of solid ionic compound is formed from its gaseous ions under standard conditions. And lattice enthalpy dissociation. Enthalpy change one mole of a solid ionic compound is completely dissociated into its gaseous ions under standard conditions. Now, all these definitions, it does look long. But more you read them, even if obviously you're not going to expect to. I've gone through these before, maybe twice before, and you just need to keep reviewing them, and eventually you'll know them like that. But what you don't want to happen is you've got your real A-level exam and you know 0 of them, because what they do in the exam, I've seen in past paper questions, they'll say give a definition, and it's never 1 mark, it's always 2 marks. So that's 2 marks, and then it'll be like, find the enthalpy change of this, or the first electron affinity of this, and you need to know the definition to construct the cycle, or how you construct the cycle. So yeah, learn these definitions. Say 2 key assumptions of pure ionic model of a lattice assumes that all ions are spherical and they have the charge evenly distributed around them. Unpolarized ions, pure ionic bonding, plus negative polarized ions, partial covalent bonding. Describing the pure ionic lattice. Now, the idea of what is actually going on. Well, the actual reality is that positive and negative ions in a lattice aren't exactly spherical. Positive and negative ions in a lattice aren't exactly spherical, and therefore positive ions polarize neighboring negative ions to different extents. Therefore, the more polarization, the more covalent the bonding. Say 3 things that happen when a solid ionic lattice dissolves in water. Number 1, bonds between ions break to give free ions. So 3 things that happen when solid ionic lattice dissolves in water. Number 1, bonds between ions break to give free ions. This is endothermic. Bonds between ions and water are made. This is exothermic. And the enthalpy change of solution is the overall effect on the enthalpy of these 2 things. Enthalpy change of solution, overall effect on the enthalpy of these 2 things. What happens when an oxygen molecule... This question even makes sense, but what I'm basically asking is, what happens because as a result of oxygen being more electronegative than hydrogen? Well, water molecules bond to the ions. Oxygen is more electronegative than hydrogen. Water molecules bond to the ions, and because oxygen is more electronegative than hydrogen, it therefore draws electrons towards itself, creating a dipole. Dipole means positively charged hydrogen atoms form bonds with negative ions, and vice versa. Negatively charged oxygen atoms form bonds with positive ions. Water molecules bond to the ions. Oxygen is more electronegative than hydrogen, therefore draws electrons to itself, creating a dipole. Dipole means positively charged hydrogen atoms form bonds with negative ions. Vice versa, negatively charged oxygen atoms form bonds with positive ions. Substances generally only dissolve if the energy release is the same or greater than the energy taken in. Soluble substances have exothermic entities of solution. Substances generally only dissolve if the energy release is the same or greater than energy taken in. Soluble substances have exothermic entities of solution. Entropy S, a measure of the number of ways that particles can be arranged and the number of ways that energy can be shared out between the particles. Entropy S, a measure of the number of ways that particles can be arranged and the number of ways that energy can be shared out between the particles. More disordered particles, higher the entropy. Large positive entropy, therefore more disordered, high level of disorder. And the idea that substances actually tend towards more disorder. Substances tend towards disorder because it's more energetically stable when more disorder. Therefore, particles move to increase this entropy. Substances tend towards disorder. That's why some reactions are feasible even when delta H is endothermic. Feasible meaning reaction happens by themselves without the addition of energy, and endothermic because increase in entropy overcomes the change in enthalpy. S with this kind of symbol, standard entropy of a substance, meaning entropy of 1 mole of that substance under standard conditions. Entropy of 1 mole of that substance under standard conditions, 298 Kelvin, 100 kilopascals. Free energy change, delta G, a measure used to predict whether a reaction is feasible. If delta G is negative, reaction might happen by itself. But and I could just see these questions like being really annoying 1 markers. Like, if students found out delta G is negative, why would the student not notice the reaction happening at all? Because the reaction might have a very, very high activation energy, or it'll be so slow you won't notice the reaction happening at all. So yes, delta G is negative, reaction might happen by itself. That's the common rule. However, it might have a very high activation energy, also slow, you won't notice the reaction happening at all. If delta H is negative and delta S is positive, delta G is always negative. And remember, delta G is delta H minus T delta S, right? Obviously, I'm not going to go through all of that as well because that's just how well you can practice it. And that's just purely doing past paper questions on gauge for energy change, the entropy, which is entropy of products minus entropy of reactants. Entropy change. Well, yeah, if delta H is negative and delta S is positive, well, delta G is delta H minus T delta S. So I've got a negative minus a positive. So then, yeah, delta G is always negative. So delta H is negative, delta S is positive, delta G is always negative, delta H is positive, delta S is negative, delta G is always positive. If delta H is positive and delta S is positive, what would happen? Well, delta H is positive and delta S is positive. Well, there's a special case. Reaction won't be feasible at some temperatures, but it will be feasible at higher temperatures. High enough temperatures. So if delta H is positive and delta S is positive, reaction won't be feasible at some temperatures but will be at high enough temperatures. If delta H is negative and delta S is negative, reaction will be feasible at lower temperatures but won't be feasible at higher temperatures.